Good day, respected external examiner and faculty members, and my academic advisor, Mr. Rakesh Babu. My name is Mustafa Ahmed Al Qatari, and it's my privilege to present my individual project for EN 8905 Energy, Environment, and Sustainability. This project assess how current and future energy system can meet regional and global energy needs in more sustainable manner. The technical foundation of this assessment is supported by my graduation project entitled Design and Analysis of an Isolated Microgrid for Rural Electrification. That graduation project provide the system architecture and component size, MATLAB and Simulink modeling control strategy and validation results used in this assessment. In this presentation, I will connect the engineering work to three wider dimensions: energy performance, environmental impact, and long-term sustainability. The first issue is the global energy access challenge. Many remote and off-grid communities still lack reliable access to electricity. In this location, diesel generators are often used as the main source of power. Diesel generation is dispatchable and technically simple, but also creates major long-term problems. It depends on continuous fuel delivery, exposes communities to fuel price changes, and requires regular mechanical maintenance. And the products also produce greenhouses, gas emissions, and local air pollutions. The main sustainability framework for this project is Sustainable Development Goal 7, affordable and clean energy. SDG 7 aims to ensure access to affordable, reliable, sustainable, and modern energy for all. The project also supports SDG 9 by introducing resilient infrastructure, intelligent control, and renewable energy integration. It's also support SDG 13 by reducing fossil fuel consumption and operational carbon emissions. Therefore, the objective is not only provide electricity. The objective is to provide electricity in a way that is reliable, affordable, environmentally responsible, and technically sustainable. To assess the energy systems, I compare a conventional diesel-only system with the proposed AC-coupled hybrid microgrid. The diesel baseline has several operational advantages. It can respond to the demands, and it's familiar to the operators, and it can provide continuous power when fuel is available. However, its disadvantages are significant. The system has high operating expenditure, continuous fuel requirements, and mechanical wear. Maintenance costs as well, and greenhouse gas emissions, and dependence on external fuel supply. The proposed alternative combine renewable energy, energy storage, intelligent control, and conventional backup. The system includes 800 kilowatts of photovoltaic generation, 500 kilowatts of wind generation, and 100 kilowatt battery energy storage system. 1.5 megawatt diesel generator remains available as spinning reserve and emergency backup. An intelligent energy management system coordinates all generation and storage resources in real time. The operating priority is to use solar and wind energy first and use the battery to balance supply and demands and activate the diesel generator only when renewable production and battery energy are insufficient. A sustainable energy system must be assessed through technical, economic, and environmental trade offs. Technically, the hybrid microgrid is more complex than diesel only systems. It requires renewable forecasting, battery management, protection coordination, voltage and frequency control, and communication between multiple energy sources. However, the additional complexity improve resilience and reduce dependence on single generator and provides faster dynamic support through the battery system. Economically, the proposed microgrid requires a high initial capital investment of approximately 1.98 million US dollars. However, the projected levelized cost of energy is between 12 and 18 cents per kilowatt hour, with an estimated payback period of approximately 1.5 to 2 years. That suggests that although the initial cost is high, the system may reduce long term diesel fuel and maintenance expenditure. Environmentally, the hybrid system reduces fuel consumption, green gas emissions, and local air pollutions. However, battery manufacturing and recycling and end life disposable must also be managed responsibly. The justified engineering judgment is that the hypermicrogrid provides a better long term balance of reliability, affordability, and energy security and environmental performance than diesel only systems. As a part of the project, I also carried out a social awareness activity. I explained the relationship between SDG 7, diesel generation, renewable energy system, and hybrid microgrid to a small group of participants in my workplace. Participation was voluntary, consent was obtained, and feedback as well was obtained. I use pre-session and post-session question to evaluate participant understanding. The results showed improved awarenesses of SDG 7 and the limitation of diesel-only generation, the benefits of renewable energy integration, and the role of battery storage and intelligent control. The activity demonstrated that public understanding is important for successful adoption of sustainable energy technologies. It also showed the engineering communication must be clear, accurate, and connected to the real community needs. In conclusion, this energy environment and sustainability assessment demonstrate that the choice of energy system must consider more than electricity generation alone. A sustainable solution must balance technical reliability, economic affordability, and environmental protection, energy security, and equitable access. Supported by technical work from my graduation project, this isolated hypermicrogrid provide a stronger long-term alternative to diesel-only generation. The system combines solar and wind generation, battery storage, intelligent energy management, and diesel backup. The simulation meet the project demand target approximately 1 megawatts and demonstrated rapid stabilization under sudden load change. The project support SDG 7 through reliable and affordable energy access, SDG 9 through resilient infrastructure and innovation, and SDG 13 through reduced fossil fuel dependence and lower operational emissions. The work has strengthened my understanding of how detailed engineering design can support broader environmental and sustainable objectives. The planning and design, sizing, control strategy, MATLAB and Simulink model, and validation result presented in my graduation project and provide the technical evidence supporting this assessment. I would like to express my sincere gratitude to my academic advisor, Mr. Rakesh Babu, and the teammate who helped me to finish the graduation project, and the faculty of Bahrain Polytechnic for their guidance and support. This concludes my presentation, and I'm now prepared for your question. You are welcome to ask anything in the comment.